Okay, so this project started for us about almost 10 years ago, I guess, so it was really just about, can we make a decent optical clock out of this particular atom? We've now gotten to the point where we've sort of reached an end on some level and starting to move that technology over to the local metrology center. And actually one of the things that I was excited about coming to this conference was to try and learn about what could I do with this clock beyond just providing the local metrology center with a better optical clock. And in particular, I was kind of interested in the sort of dark matter alpha variation type of physics. And when I heard how open that problem was, it sounded like looking for Waldo in a library full of Waldo books, and Waldo might not even be there. So the question that comes up there, and it was sort of mentioned in the earlier talk, is how do you know your clock is really working as well as it should, right? So if you're trying to do height referencing or alpha variation, how do you know that you can actually do that, right? So with that in mind, let me tell you about lutetium. I'm going to tell you what I can do, what I think I can do, and then hopefully shed some light on what I can do about that problem, right? Okay, so lutetium has a fairly unique atomic structure. It has a low-lying set of D levels here, which gives us access to multiple clock transitions. We label them by the wavelength that the clock transition is at. I will often refer to this first one here as the primary, and this one here as the secondary. Both of those clock transitions have nice systematics, right? So able to get reasonably high accuracy performance, or at least I would claim so. Most of our work has been concerned with the 3D1 level. That has a lifetime of about a week, and it also has an exceptionally low blackbody radiation shift, so temperature is really not so much of a problem for this particular clock. It has a very large hyperfine structure, and because of that long lifetime and also the very low magnetic sensitivity of those levels, we can also do high resolution microwave spectroscopy on that level, which helps us to assess the clock and the various systematics that come with it. Of course, as was pointed out, this has a J quantum number, which means it has electronic shifts, which are normally problematic. But as it turns out, if you average over all three levels here, so you average not over Zeeman pairs, but over the hyperfine states, then those shifts actually magically cancel for us. So that's true, provided the nuclear spin is larger than the electronic spin, which is the case for lutetium. The way in which we do that averaging, there's multiple ways you could do it. You could just simply probe over the different optical channels and form your average in that way. But we do it in a way that sort of makes it convenient for us. We basically take your usual Ramsey experiment, and then you interleave it with microwave transitions, which sort of shunts it around the upper states, and sort of you spend the same time in each state. Then what happens is you get a sort of an average frequency out of that. So the idea is that the clock frequency is the average of these six, which I can rewrite in terms of the splittings, but that's how I do it in the lab. And if the microwave frequencies are not quite right, the magic of the Ramsey experiment is that the optical frequency gets offset to compensate that, and that then represents the average frequency that we're after. So in the lab, we've got our laser frequency probing that level, and then we offset it by these microwave frequencies to get our average. And of course, that's normally done in bookkeeping. So that's just to bear in mind how that happens, and I'll sort of mention later how that factors into things. As with the earlier speaker, we do not have the best laser in the world, so we use correlation spectroscopy to do all of our experiments because it gives us essentially better stability to make measurements and so forth. But we're ultimately always limited by that. As was also pointed out by the previous speaker, as a single ion, we're limited in that stability. So at some point we have to address that as well. So I'm just going to sort of if I'm going to make a claim of what I can do, I have to at least give you some faith that I can actually do it, right? So I want to just give you a sort of a glossy hand-wavy thing of what we can actually do in the lab. If I take a measured clock frequency, I can very glibly say it's basically a true clock frequency, and it's offset by some shifts that are basically a property of the atom times the environmental factor, and I just have to figure them out. That's what my error budget is. So in lutetium, I'll concern myself with the biggest ticket items, right? So the first one is your applied DC field, so that gives rise to your standard sort of Zeeman shift. That's never a problem for an optical clock, right? It's just by the way in which you actually measure it, it's never the limiting thing on your error budget. And in the clock cycle, we actually measure that magnetic field on every clock cycle, so we can keep track of how that field is varying by the small amounts, and that's why we correct it. And in fact, I don't even put it on an error budget. For lutetium, and for any clock that has a hyperfine structure, you have to worry about the AC magnetic fields that arise from the fact that the trap is being driven by a voltage. It's basically a capacitor, so you get these currents. Those currents give rise to a shift. And in our case, we are sensitive only to that perpendicular component, so we have to measure that. And the way that we measure that is with barium. We tune our Zeeman shift so that it matches the trap drive frequency, and that gives rise to a coupling shown here. Then when we drive that clock transition, we see an outlet-town splitting, and that can very accurately measure that effect. And so then we get a very accurate handle on that shift, and then we can characterize it pretty well. It's also very stable, right? Because it's to do with the stability of your trap. If that's changing, it means your trap frequencies are changing and all that kind of stuff. I said that we average away the electronic angular momentum shifts. That's always in a clock. That's true to some degree, right? So there's always this sort of residual coupling to the upper levels, and that gives us what's called the hyperfine mediated quadrupole moment. It's really small, so for our typical trapping parameters, it's at the level of 10 to the minus 19. But we can measure it, again, by measuring with barium. Then we can scale a quadrupole moment, and then that gives us some sort of measure of what that is on the clock. The other things are, of course, micromotion. Micromotion, we have a secondary clock transition, so we can probe that very accurately. There's an AC Stark shift. We use Hyper-Ramsey to sort of mitigate that, and it's not much of a problem. And the BBR shift, as I said, is pretty small. What's not listed here, of course, are the relativistic shifts, which are the gravitational redshift, which you kind of want. And then there's the thermal motion, but it's a heavy ion, so those things tend not to be so much of a problem. Right? So what can we do, right? Or what, more to the point, what have we done, right? So as I said, I don't put that DC magnetic field shift on there because it's just a typical number. That would be at the level of 510 to the minus 20 for an uncertainty, so I don't care about it. The other one that's not there is the BBR shift. And just to give you an idea of how insensitive we are to temperature, if I had a temperature of 30 plus or minus 5 degrees, which I think is something that we could achieve, that's a 10 to the minus 18 shift, but the uncertainty is at the low 10 to the minus 19. So we get down to a pretty good situation, right? So we're at this sort of low, mid 10 to the minus 19. If I look at what the problems are, so on one clock we have this larger part from the second order Doppler shift. That was from a heating problem in the trap. We have now fixed that heating problem, and I'm hoping that they're running the next comparison, right? So the next one on this error budget would be the residual quadrupole shift. That's there and not there because we measured it in this trap and we haven't measured it in this trap. So if we measure it, we should be able to push that one down. We didn't measure it because we're limited by a measurement precision. The final one that is this excess micromotion, and Tanya talked about that, so we sort of know what the deal is here. We don't measure this all the time, right? So it's something that we sort of only measure intermittently, so it drifts with time, and so that sort of bounds the worst possible case scenario. Since we're now looking at moving this technology to the Metrology Center, obviously we have to automate that process, and so once we automate that process, we don't see a problem with pushing that down to the sort of 10 to the minus 19 level. Right? So then if you take those main shifts out, you're basically limited by this one that's called this microwave coupling. That's an error that's associated with the imperfections of our microwave driving in the upper state. So if that was my biggest problem, I would then go back to the usual interrogation technique where I don't have that problem. So what I would say then is, I think in principle we can push that down to the low 10 to the minus 19. Right? So how accurate is a lutetium clock? Controversially, what I would say is I'm an experimentalist, so that is my uncertainty, the 3.7 times 10 to the minus 18, because that's the comparison that I've made, and that's how good I can get it. Right? I would say that comfortably, if I integrated for 10 times longer, then I would comfortably get down to 10 to the minus 18 or slightly below. If I could go again more, I think I could comfortably get to mid 10 to the minus 19. And if you really ask me to push it, maybe I can get to 10 to the minus 19. Right? And I guess what I would say is, I think that comparison between two identical clocks is important. And this is the reason why. Right? So this is the thorium clock budget, and this was sort of presented at the workshop earlier. And the numbers are also getting down to that 10 to the minus 19. But if the experimentalists went and built this clock, that's the error budget they would produce, and they would say that's our accurate clock, and then they'd start making comparisons with other clocks, right? But what's missing on this error budget is that one that I mentioned before, which is the shift because of the hyperfine structure from the AC magnetic fields. And as it turns out for this clock, that would swamp the error budget, right? And so I think you've got to be careful about how good you say your clock is if you're not making these comparisons. And what I thought was funny, when I was Googling this to try and find this error budget, I found this, the thorium nuclear clock, the world's most accurate clock, and I thought, at the very least, we have to build it first, right? That's got to be a minimum standard, I think, for how these things are done. But of course, you've got to be careful what you say to the media, right? Because the media will say whatever they want. Okay, so as I said, I would say I'm limited to 3 times 10 to the minus 18, and why is that? So as it was sort of pointed out before, so this is your formula for stability. You don't usually see the numbers at the top. The root 2 is because I made a good comparison. I've got two clocks, they both contribute. A factor of 2 there because I'm trying to do the best I can, but I lose some contrast. So that's what I get. So if I take my 1 ion, I integrate for a fraction of a second, I average for 2 days, then I get my 3 10 to the minus 18. And to be honest, right, the 2 days is actually spread over a longer period of time because things don't work. Sometimes things break down and you have to fix them and whatnot. But as was pointed out in the last talk, at the end of the day, you need more ions or a longer interrogation time. So in terms of that formula there, that's the only things that you can really change. You have to average for longer, or you want to improve those numbers. So this is work that we did quite some time ago. It was really just sort of a proof of principle to know how well could we possibly do with that. And so as was pointed out in the previous talk, you have this sort of inhomogeneous broadening when you start looking at a large number of ions. Now, it was a proof of principle, so I wanted to take the simplest possible case, which is 3 ions. So Tanya already mentioned about micromotion magnetic fields and AC magnetic fields, and I would probably say that they are universally true for all of the different ions, right? What is not universally true for us is the quadrupole moment. We average it away, but not between ions, right? So we have to actually take that into account. Otherwise, that will smear out our line, and then we have a mess, right? And so the basic idea then is, also as Tanya pointed out, is that this quadrupole shift gives rise to a shift that's differential between the ions. So you have the quadrupole moment, which is a property of the atom. You have this angular dependence, which is to do with the angle between the B field and the crystal axis. You have a Krebs-Gordon coefficient, and then there's the scale factor, which is which ion are you in the crystal. So obviously, if I've got a 3-ion crystal, the ones on the outside are the same, but the one in the middle is obviously different, and so it will get a different shift. But as I said, lutetium gives us this excellent ability to actually look at microwave spectroscopy here, and because these C factors are different, we will see a shift of this because of that quadrupole shift. So here we've got a 1-second Ramsey time. We see that the outer 2 ions have exactly the same frequency, but the red one, which is the middle ion, that's shifted differentially because of that factor. Right? And the way that I would say it with clocks is, if you can see it, you can fix it. Right? This would be the way that I would view it. We can also see this when we look at the optical transition. It's basically the same thing, but again, we look at this with correlation spectroscopy. So we have, if we take exactly that same scenario, we know that the outer 2 ions should be the same. So we see the outer 2 ions, they don't change at all as with respect to the Ramsey time. But for ion 1 compared to 2 or 2 compared to 3, we know that there's a shift there, so we see this sort of frequency difference manifesting in the Ramsey time. Right? We see a slight difference in that frequency, and that is actually turns out to be because of a magnetic field gradient along that chain. But of course, we can see that as well on our microwave transition. And again, if you can see it, you can fix it. So you could fix up that gradient if you thought that that was a limiting factor for you. Again, if you see it, you can fix it. So you basically then change that angle, and you try to tune that angle till you get it to be something where this ends up being 0. And so here we have a 5-second Ramsey time, and we've brought those fringes more or less into alignment. The limitation there is the patience of the postdoc doing the experiment, because these experiments do take some time to actually run. That's not to be critical of my postdoc, right? I should make that clear. What I would say here is this could be an automated process. So you could automate that to bring those things into line and have a computer do that, as opposed to your postdoc. Right? So once we bring those into alignment then, and we now look at our interrogation time, we see this sort of, there's some sort of overall decay that we can't quite account for in terms of any small frequency differences. And so that's sort of some sort of decoherence that we suspect is probably due to heating or something like that that's causing things to belly up. But at the level of this experiment, I would actually claim that it seems reasonable to us to think that we could at least get to t is equal to 20 seconds in order of running a clock. Right? So in terms of what I think I could do, I would say it's not unreasonable to think that I can go to 10 ions with a 20-second interrogation time with that same 2 days of integration time. That will bring me down to this low 10 to the minus 19, which was also consistent with what I think I can do based on my error budget. Right? I see no point in trying to go more than this until my error budget can be pushed down further as well. Right? And so that's the way that I sort of see things there. Now, I think that the true advantage of lutetium is this 2 transitions within the 1 atom, right? And so the basic idea is this. So if I have got my frequency here, it's got this sort of P dot E. If I make an in situ ratio measurement, right, that just manifests as the difference in these properties dotted with that environmental factor. But that environmental factor is the same for those 2 transitions because it's the same ion sitting in the same trap, right? And so therefore, what I would say, if I think about an error budget for this ratio, that error budget is the environmental factors and these properties, but they're also part of your error budget for your 2 transitions, right? So as soon as I've got my error budget for my 2 transitions, that error budget for the ratio is set in stone. So that ratio now becomes a figure of merit for my clock performance, right? If I say my two transitions are accurate to 10 to the minus 18, then it must be true that that ratio now is also accurate to 10 to the minus 18 in the same way, right? Now, of course, you have to worry about what happens when you take that difference. Are you getting up to mischief when you do that, right? So as it turns out, I would say that the magnetic field is not a problem. So the two transitions have sort of not quite equal but opposite signs of that shift, and so they don't cancel when you take the difference. This magnetic field shift here is actually much larger for the 3D2, so it's limited by that 3D2, but again, we have a very accurate measure of it, so I don't think that's a huge limitation. The hyperfine mediated quadrupole moment, as I said, for 3D1, we have a combination of measurement and calculations from Mariana to tell us what that is. We don't have that for 3D2, and I guess I would have to ask Mariana to do more calculations for me, but then I feel like Oliver Twist going to need more calculations. But I would say that I don't, this shift is already at the level of low 10 to the minus 19, so I'm not sure that it's going to ever be a limitation for us in reality. So these shifts here are basically the sort of same. The AC Stark shift is not a problem for 3D2. And then the only thing left is the BBR shift, and that's more significant on 3D2. That's sort of on the order of the sort of Indian clock number. It's a factor of 2 larger, so something like 3 times 10 to the minus 17, so it's manageable. So what I would say then is that this ratio as a figure of merit for my clock performance, it's the same level of accuracy that I have for the two transitions, but it's limited by the BBR shift, right? So if I wanted to make a clock system that I could trust at that level and know that everything is good, I would do it this way, right? So I would take my two clocks, one at CQT and one at our local metrology center, but put them at liquid nitrogen, right? So at liquid nitrogen, that BBR shift goes away to the level of 10 to the minus 19. So to the level of accuracy that I think I can achieve with my clocks, I now have those two things where I think that they should be the same. So I measure that in situ ratio to whatever precision I can get, and I would say those two ratios have to agree. If they do not agree, then that means that those two clocks are not performing at the level that is being claimed. So something is wrong with the clock, and you have to fix it, right? Admittedly, it could be a property of the atom is wrong, but given the properties that exist there, it's not likely to be the ones that are problematic. So now that I've got my two clocks, I know that those two clocks agree. I now make my comparison between those two clocks on my primary, and that there is now something where the only difference between these two clocks is the gravitational redshift. And so now I get that gravitational redshift. If you still don't believe me, we can compare on the secondary and confirm that that is the case, right? Now, perfect, actually, so great. I told you I wouldn't be over time. So this number that we measure is now a global parameter. It is the effective zero temperature ratio, and so now we no longer need to be at zero temperature. If I take two clocks that are not at zero temperature, I measure the ratio, I can compare that to the known zero temperature ratio, and that will now determine the temperature of the individual systems. But I've lost my figure of merit from my clock, right? So I compare on my primary. When I compare that on the primary, there's a small temperature correction, but now I get what is the gravitational redshift between the two clocks. I can then compare on my secondary transition, and that will now confirm the temperature and the redshift that I get for those systems. So that gives me a self-consistency check for how those clocks are actually performing. Now, in terms of the alpha variation versus, or the dark matter search thing, one thing that is interesting with lutetium is that each of these transitions is sensitive to an alpha variation, but the ratio is not. So my ratio maintains my performance standard, and so if I was to see a variation on my individual transitions, but my ratio is solid, then I would have a lot more confidence that what I'm looking at is a feature of our universe as opposed to something wrong with my clock, or at least that's what I would claim. Now there is an obvious problem, and that obvious problem is, how do I see a change in the frequency of my clock? I need to have something else to compare to. And so the question is what would I compare it to? And ideally, I would want something that is very much like lutetium, something that has those two clock transitions that are insensitive and so forth. And so it's, what do I do with that, right? I think it's true that I could do the same with 3 clocks, right? As long as I have 2 other clocks that are, for example, insensitive to an alpha variation, then if I compare all 3 clocks, I could try and figure out what's actually going wrong. But that requires me to build 3 clocks, and I was happy enough to build 1, right? If you find me another one like this, I would be probably happy to build 2. I don't think I could convince the funding agency to give me the money to build 3. So, as I said, that's what I think I can do with lutetium, and so that's the sort of level of accuracy that I think that I could get out of the clock, and to what level that can actually be done. I think, as Tanya pointed out, technology is always going to improve, right? So if you go to more and more ions, I think that this clock has the capability of continuing to hold that line so that you can get down to whatever accuracy you think your error budget can do. Okay, with that, I will finish and just thank my group. Actually, many of the group members here are actually new, so the ones that I would like to thank in particular are Kyle, who's been with me since the very beginning, and Ratikorn, who is now at the Thai National Metrology Center, and he was sort of did a lot of the work to sort of get the clock to this sort of level of performance. Okay, so anyways, thank you.
Thank you for the very nice talk. Open questions. I mean, we can start.
Murray, just very exciting, this ratio measurement. Can you do the clock transitions simultaneously? You know, your 804 and 848. Can you put them all 3 states in coherent superposition, or you have to do them sequentially?
I can put them in some sort of weird superposition, but could I maintain clock performance and do that? So I would definitely be thinking of measuring them. You'd have to measure them, you know, I would interleave them, right? And
yeah,
so
right now you interleave them, right? You're driving them independently.
Yeah,
but it would be actually super exciting if those both clocks actually running at the same time.
Yeah, and as I said, I think that's certainly not, we can do that. We can put them in a, so you're saying like the ground state has some population and the upper 2 states have the, share the population as well, so it's a 3-state thing, right? That I think we can do. I guess what I'm asking then, what I'd have to ask is, what would that mean in terms of a measurement and how that would factor into things? And does that depend on how the quality of the superposition that I've made? I don't know the answer to that, so.
People are talking about the gravitational effects and so on. Imagine you have these 2 different mass defects simultaneously running. If you really were able to achieve multiple ions in the sense, you can actually do something in neutral atom, which is hard to do, where we have multiple clock transitions, but it's very hard to find a magical wavelength that works for all of these clock transitions.
Yes.
You have the Lorentz force, which is separating those effects, right?
Yeah.
So if you can actually do this, it would be quite exciting.
Yeah.
On technical side, I thought you mentioned the black body radiation effect is tiny, and especially the uncertainty is at 10 to minus 19 level, even at a room temperature.
Yes, for the one transition. For
yeah,
the other transition, it's not.
Oh, I see.
Yeah, so the other transition, it's more like 2.7 times 10 to the minus 17. And so that means you would have to have temperature accuracy of, I think it's something like 3 degrees to get to 10 to the minus 18, I think.
Yeah.
And so to get it really down, you have to do something with that. So that's why I was saying I would take it out of the equation by going down to a colder temperature.
Cryogenic, but the measuring temperature to a Kelvin is not hard. Is it the reason why you think it's hard is because of you are doing IF trap and there's some effective temperature you're not certain about.
And it's just,
okay.
It's just it's a confidence thing, right? Like, let me just take it out of the equation so that then I can be confident that it's dealt with, right?
Okay, thanks.
Yeah.
Thanks, Murray, for the great talk. I had maybe 2 short questions. I was curious about the BBR shift. It didn't, in the comparison of the 2 clocks on the same transition, I was curious why the BBR shift wasn't included in the uncertainty budget.
Because we can't measure the temperature in our current system, but in order to affect the clock at that level, they would actually have to be different in to the measurement precision. They would have to be different by about 100 degrees, which I think is unrealistic. And even at the level of 10 to the minus 18, they would have to be different by degrees. And the number I know in my head is they have to be different by 20 degrees to get 510 to the minus 19. So it's just, you know, based on the fact that they're similar construction, driven with similar levels of power, I just don't see how they could be at different temperatures.
Yeah,
so, But as an
I wonder though if you could put some bounds on it, like.
Yeah. So if only to the following level, right? If I took the worst case scenario of all of the power being delivered to the electrode and looked at the thermal chain to my external vacuum system, I think I could say, and I think it's something like 35 degrees plus or minus 10, right? But I wouldn't call that an assessment. I just, you know, my measurement precision is 3 times 10 to the minus 18, so I don't care beyond that, right? So I would stick with what have I actually experimentally done.
Thanks.
But I should say we do have another trap that's on the table, ready to be put on the table, and we're just waiting for the thermal sensor to put that on the electrode so that we can at least say something intelligent, right?
Yeah, and then my other question was for like the 3-ion or in the future more ion crystals, how homogeneous do you think that the ACB field is in the trap? Is that something you've measured or have thoughts on?
Yeah, so I believe that was measured for the 3 ions in that experiment when we measured the quadrupole moment by this thing and we accounted for that there. I don't recall offhand, but of course that's only over plus or minus 10 microns, and so there isn't a significant difference there. If you're talking about the kind of things that Tanya does, you know, that could be massively more. But it is a shift that it can be accurately measured, so even if it's reasonably inhomogeneous, you can still get it accurately. And you've got to compare that with your interrogation time. As long as it's not smearing out your line, then I think it's less of a problem. So, yeah.
One question regarding the quadrupole shifts in these chains. So is it in your system an option to try to sort of average, like in a coherent way? There's this idea to have your field, your magnetic field, rotate through the course of the Ramsey interrogation, or would that come with many other problems in your setup so that you wouldn't really win?
So this is what I would worry about is if I'm doing that rotation, am I doing that rotation the same tomorrow as I am today? You know, there's hysteresis in those things and that kind of thing, right? I think the idea of doing 3 orthogonal directions, that is possible, but not for our current implementation. And the reason for that is the microwave transitions. We crudely do that right now. And so if you change the magnetic field, you change the microwave couplings. And so then you would have to recalibrate everything for those different directions. But when we do this, we optimize the pi and try to suppress the sigma because that's another particular potential error. So it's a practicality thing. I think the short answer is yes, you could do that, but whether that's actually technically better than just simply doing the averaging over the three transitions. Averaging over the three transitions also gets rid of magnetic field effects as well. So.
Should highly charged ions apply for the position of the second clock? It could solve numerous problems, because then you actually have all of the transitions. There are plenty of them with two transitions, and then your black body shift problem goes away because everything has to be at 4 Kelvin anyway.
Yeah. So yes, anyone may apply. I'm an equal opportunity employer. So just to make sure that I'm clear about what I mean, right, is I'm a distrustful person by nature, so I even distrust myself. So this ratio gives me something that is a figure of merit that says I'm doing my job, right? So if you're talking about a highly charged ion with one transition, I would say, so if the highly charged ion has two transitions in it, then I'm good, right? I'll entertain it.
I think we would have one with 3 transitions.
Okay, then that sounds great. Please apply.
Any more questions? If not, let's thank the speaker for all the sessions in the morning. We have lunch now.